Welcome, everyone. For today's prep, we're going to start to look at radioactive decay. And this is another application of our exponential functions. And first of all, we're going to start with just a little bit of terminology. We're not going to get too much into the physics and the chemistry of how this process actually works. We're going to get more into we're going to look more at the mathematics of it. All right, so what do we mean by radioactive decay? Well, this is the process in which an unstable nucleus of a radioactive element decomposes by emitting particles. So essentially, the little diagram to have in mind is we're going to have some radioactive element, and we'll see some examples of these in some of our work. So we've got this radioactive element here. And at the atom level, if we have a radioactive, the nucleus of a radioactive element, what happens is this nucleus breaks apart, and it breaks apart, and what it produces some new material. Plus, it also emits some particles. So we're going to have some new material, some new element, and a lot of times this new element is also itself radioactive. And then there'll be some particles that get emitted as well. So this is, a very abridged version of what happens. Now, how do we kind of quantify this process? Well, one way we do this is with what's called the half-life. So this is the amount of time that's required for a given quantity of a radioactive element to decay until one half its original mass. So we start with a certain quantity, and the half-life measures how long it takes until half of that radioactive element or our radioactive sample is gone, replaced by either this new stuff or maybe that stuff decays then too. But how long does it take for half of our initial radioactive element to decompose? All right, so let's look at an example. We want to look at the mathematics of this. So we're going to have a little motivating example here. So let's suppose that we have some radioactive element, and this has a half-life of 1 day. So every day that goes by, our sample is going to be essentially cut in half. Let's suppose that our sample starts with an initial mass of 1,000 milligrams, and we want to figure out how much of the mass is going to be remaining of this radioactive element after 3 days. All right, so let's look at day 0. Day 0, we've got our whole radioactive element here. So this whole thing is radioactive. So the whole sample is 1,000 milligrams. All of our radioactive sample there. All right, so we're gonna go from day 0 to day 1 and watch what happens. So if we remember, the half-life of this is 1 day. So what happens is half of our sample is still going to be there. So we're still going to have half of this is still going to be our radioactive element, but the other half has now decayed into some other material. So what we have is now half, 500 milligrams of our radioactive sample. Okay. So now let's watch what happens when another day goes by. So now our sample is, when we go from day 1 to day 2, this is now our radioactive sample. Look at it all glowing there. And this is going to get cut in half. So now this half becomes our new material, whatever that is, and half of that is still our radioactive sample. And then the half that had decayed from before, that is still, some other material. It's not our radioactive sample. All right, so how much is going to be left here? Well, we're going from 500 and we're halving that. So we're going down to 250 milligrams. Now, what about on day, let me get out of here for a second. What about on day 3? How much are we going to have left by day 3? Well, again, we're looking at our day 2 sample. So here it is. And this is going to get cut in half. So our radioactive sample by day 3 is going to be this little wedge. And the other half decays to some new material. And then we still have our other material from the previous day and the day before that. And, maybe this is doing something else, but this is not our radioactive sample. This is no longer our radioactive sample. This is not either. All right, so how much do we have? How much do we have left at this point? Well, we went from, again, we're halving this. So we're cutting this in half. So we're down to 125 milligrams. So each step along the way here, what we're doing is we're multiplying by 1/2. And whenever we have this kind of repeated multiplication, that is an exponential function. But now the fact that this number that we're multiplying by is less than 1 means it's going to be a decaying exponential function. So if we plot the corresponding exponential function, we're starting with 1,000. So we've got our first data point. Then day 1, we've got 500. Day 2, 250. And then day 3, 125. All right, so what is this exponential function? We want a formula for this. And it's going to be very similar to our exponential growth formula. In fact, it's basically the same thing, except our k value in this case, for exponential decay, the k value is going to be less than 0. It's going to be a constant. So k is still a constant, but it's going to be less than 0. So for exponential growth, k is positive. For decay, it's negative. Now, when we talk about exponential decay, usually we want to really stress the fact that that constant is negative. So a lot of times we rewrite that constant k in the form negative times lambda, just to really stress that we're dealing with a negative in the exponent there. And the number part, lambda, is called the decay constant. And just like before with exponential growth, this P0 in front is going to be our starting population or our starting mass. So sometimes we might also write exponential decay because we're talking about mass. We might also write this as, call this function m of t for mass. So we might say our initial mass and then e raised to the negative lambda times t. So what this function p of t does, or if we're calling it m of t, it describes our mass at time t. And just like with exponential growth, there is a differential equation that this function satisfies. So the rate of change, the rate of decrease in this case, of our population of radioactive nuclei is proportional to the mass of our sample. So this is the same differential equation we looked at with population growth. So it has basically the same solution, except now that k value is negative. So let's try an example. The decay constant for strontium-90 the lambda value here, is 0.0244, and this decay constant has time being measured in years. And we want to know how long it will take for a quantity, just some general quantity of strontium-90 to decay to 1/2 of its original mass. So essentially what we're trying to do here is we're trying to figure out the half-life. Okay. So what information do we have? Well, we know we're dealing with radioactive decay, so we can write down our radioactive decay formula, and we'll use the negative lambda version just because we have information about lambda. So let's write that one down, 0.0244. And we're trying to figure out the half-life. So if we look at this equation, there's a lot of things we don't know. So we don't know our initial mass. We're not told it. We're just saying how long does it take for any quantity to decay to 1/2 its original mass. So we don't have this. Now what about P of T and T? And actually let's just call this P just for short. Well, what are we trying to figure out? We're trying to figure out the half-life. So even though we don't know how much we're starting with, we're interested in knowing when do we end up with half of what we started with. So this is what the half-life means. We're trying to figure out how long it takes until we get half of what we started with. And we don't know T either, so that's really what we're trying to figure out. All right, so let's put these pieces in, put them all together, and see what we have. And actually, this is going to be enough. So T is what we're trying to figure out. We're trying to solve for T here. So if we put the pieces together, our future value here, our P of T, is 1/2 our starting population, or our starting sample size, 1/2 times the initial mass. And we have our initial mass over here. Again, we don't know what that is, so we're just leaving that in place. That's fine. And we do know what lambda is, so I'll replace lambda with my decimal. So 0.0244. And I don't know what T is. And again, T is what we're trying to solve for. So that's the goal here. Now you might be wondering, how can we solve this equation? Because there's two variables that we don't know. Well, it turns out that because our initial mass is showing up on both sides of this equation, we can actually divide by it. So we actually don't even need to know our initial mass here, because it's going to cancel out. So it's going to cancel out from the left and cancel out from the right. So when we do that simplifying, we end up with 1/2 is equal to E raised to the negative 0.0244T. And what we're going through now, we're going through the usual motions of solving an exponential equation. So going back, this is just an exponential equation that we're trying to solve. We've done this a few times now. So we want to solve this exponential equation. We were able to cancel off the initial mass from both sides. So we get it to this point. We've got our exponential term all by itself. So now we can apply the natural log to both sides. So we can apply it to both sides of our equation. And when we do that over on the right, the natural log and the E cancel out. So we end up with natural log of 1/2 equal to negative 0.0244t. And then finally, we can solve for t by dividing by that constant. So we end up with t is equal to natural log of 1/2 divided by negative 0.0244. And let me see if I have it. I just want to see if I have this as a decimal. Yes. So this is approximately 28.4, and our units here are years. Now you might be wondering, where does this negative go? Well, natural log of 1/2, if you plug it into your calculator, is going to be a negative value. So this ends up being kind of like a double negative, so it ends up being positive. All right. So we're going to practice a few more of these in class, but this one's interesting because what this shows us is that it doesn't really matter how much material we start with. It's going to take, the half-life is going to be the same regardless. So whether we start with 1 milligram of our radioactive element or whether we start with 1 kilogram of our radioactive element, it's going to take the same amount of time in each case for it to decay to 1/2 of whatever we started with. So that's kind of an interesting fact there. All right, so we'll see you in class. Bye-bye.